Hello and welcome to my science tutorials. In today's video, we want to look at how to form all possible structural isomers of alkanes from a given molecular formula. Before we begin, if you are new to the channel, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So let's begin. So we want to first of all start by looking at a 2-carbon alkane. So we have, for a 2-carbon alkane, the molecular formula is what? C2H6, which we can obtain from the general formula CnH2n plus 2. So because we are looking at a 2-carbon alkane, if we substitute the number 2 in place of n over here, okay, so the number of carbons is 2. If we do the substitution, we are going to get this formula, which is C2H6. So what we want to do is to look at the carbon-carbon connectivity, or the carbon-carbon framework, which we sometimes also call the skeletal system of the compound. Now, the carbon-carbon connectivity of a compound determines the physical and then the chemical properties of that particular compound. For instance, we may have, let's say, a 5-carbon atom, for instance, and you may think that will just be a pentane, but no, there are other likely compounds out there that may also have a 5-carbon framework, but the connectivity of the atom or the carbon-carbon connectivity may be different, or sometimes their orientation in space may also differ. Because of this difference in the orientation or the connectivity of the carbon atoms, their compounds tend to exhibit different physical and chemical properties. So we don't just look at the molecular formula of a compound and assume this is what a compound is going to be. No. So in this tutorial, I want to look at all possible isomers, or all possible compounds that may be derived from a given molecular formula. So for a 2-carbon alkane, we see that we can have the carbons connected directly to each other, and this is the only way that these 2 carbons can be connected to each other. Now you may decide to add it this way, okay, so that they will go this way, or you may decide to write it this way. But in both cases, or in all cases, you can see that these 2 carbons are directly attached to each other. Okay, so if we add the number of hydrogens over here, so this is 4, 5, and 6. The same way here, if we add the hydrogens here as well, okay, you get to realize that let me just ignore this for now. You get to realize that we have carbon 1, carbon 2, and this is also carbon 1, carbon 2. So if you want to name this compound, a 2-carbon alkane start with the prefix "ete", and then we add into it, which is ane. So this is an ethane, this is also an ethane. Okay, so we get to realize that whether the compound is straight like this or it is facing upward, it is still ethane, since the longest continuous carbon chain is 2 carbons and they are directly attached to each other. So which means for the molecular formula C2H6, we only have one possible isomer for that particular compound. Now let's look at a 3-carbon chain atom. So we have N is equal to 3, so it means our compound is going to be what? C3H8. Now let's look at all possible isomers that we may have for this particular compound. So first of all, the normal general way of writing a C3H8 carbon is when we have the 3 atoms, which are the carbon atoms, connected to each other directly, forming a long chain. So let's write that. We have the first carbon connected to the second carbon connected to the third carbon. So we can now add our hydrogens to form our compound. Okay, now this is one way of drawing the carbon-carbon connectivity of the framework or of the compound C3H8. Now let's look at other frameworks that are possible. Okay, so we are just assuming, we don't know yet. So what if I have just 2 carbon atoms and I add the third carbon coming down, or I have, let's say, 2 carbon atoms and I have the next carbon attached to the first carbon over here? What is that going to give me? Okay, so we have this, or we have this way, or we have this way, or we may have, let me say, first carbon and second carbon, and then I add the third carbon to the top over here. Okay, so let me just write the condensed form. This is going to be 2, this is going to be CH3, so this is CH3, this is also CH3, this is H2, this is H3, H3, H2. Alright, so we get to realize that for this particular framework or carbon-carbon connectivity, we have the 3 carbon atoms directly attached to each other. Okay, so this is carbon 1, this is carbon 2, and this is carbon 3. So this compound, an alkane with 3 carbon atoms, is what we call propane. Okay, so this compound is propane. Now, if we look at this compound really well, and we want to count the longest continuous carbon chain to name this compound, we get to realize that this is carbon 1, this is carbon 2, and this is carbon 3. We don't just say this is carbon 1, this is carbon 2, and then this becomes a substituent. No, this is the longest continuous carbon chain in this case. Okay, so this is a 3 carbon atom, okay, and 8 hydrogen. So this is also what? Propane. Okay, so if we look at this guy also, well, we get to realize that this is also carbon 1, carbon 2, carbon 3. Or even if we go in the reverse way, we are still getting a 3 carbon compound. So this is also propane, okay, and this is also propane. So which means it doesn't matter how you draw a C3H8 carbon, it doesn't matter how you try to change the carbon-carbon connectivity. In the end, you get to realize that all 3 of the carbon atoms will be directly connected to each other in one way or the other. So in the end, there is only one possible isomer for a C3H8 carbon atom or an alkane. So that only possible isomer is what we call propane. Okay, so there is only one possible arrangement of the bonding atoms, as I said earlier on. That is the third carbon atom, which is this guy that I have over here, the third one that I'm adding in different positions to see if we can have possible isomers. That third carbon atom has to be attached to either of the 2 carbon atoms, forming a 3 carbon long continuous chain. Okay, so we can observe that no matter the CH sigma bond that we rotate, okay, it doesn't matter where we place the third carbon, we still have the same 3 carbon compound with all the carbons bonded to each other in a straight line. This implies that from carbon, let's say alkanes with carbon 1, alkanes with 2 carbons, and alkanes with 3 carbons, okay, that is from methane, then ethane, and propane. Okay, so it means methane, ethane, and propane are unambiguous and only have one possible structural isomer. So what it means is that from carbon 1 to carbon 3, that is alkanes with carbon 1 through to carbon 3, only have one possible structural isomer. Okay, so if it is ethane, it's just ethane. If it is methane, it's just methane. If it is propane, it is just propane. It doesn't matter how you try to change the carbon-carbon connectivity or framework, you still get the same compound. Now, what happens if we have a 4 carbon alkane. Okay, then we have a different story. So let's look at that. So we have a 4 carbon alkane, so N is equal to 4. Now if we do the substitution into the formula, we are going to get a molecular formula for the compound to be C4H10. Now from this compound, okay, there is the possibility of having more than one possible carbon skeleton. That is, the basic and common structure is the straight chain alkane having 4 carbon atoms connected to each other. Okay, so let's look at the number of possible isomers that we may have for this compound. So let me start. The basic of basic is always, when you start, try to draw all the carbon atoms connected to each other in a long chain. Okay, so we have carbon 1, carbon 2, carbon 3, and carbon 4, all connected to each other. Okay, so let me add the number of hydrogens that we have. So we have 3 here, we have 2 at the middle, another 2 at the middle, and we have 3 on the last carbon. So we have 3 here, making 6, 7, 8, 9, and 10 is okay. All right, so this is the first way that we can draw the structure of this compound. Now let's look at other possible ways of drawing this compound. All right, so I can decide to have just 2 carbon atoms, and then I add the 3rd carbon here, and then I add the 4th carbon here. That is also possible. I can decide to have 3 carbon atoms, and then I add the last carbon over here. Or I can decide to do the reverse way, have 3 carbon atoms and add the 4th one over here. Or if I like, I can decide to have 2 carbon atoms with the 4th, the 3rd, and then the 4th carbon atoms pointing upwards. Okay, so let me add the number of hydrogens over here. This becomes 2, this is 2, this is H3, this is... All right, so we can see that writing the compound, okay, we can write the carbon-carbon connectivity in all these possible ways. Okay, so this is one of the ways of writing the carbon-carbon connectivity. Okay, so let's look at something. Let me use green. So we realize that over here we have carbon 1, carbon 2, carbon 3, carbon 4. There is no substituent, so we have the longest continuous chain is 4. Okay, so when we have 4 carbon atom and then the compound is an alkane, the name is what? Butane. Now let's look at something. Let's look at this compound. If we look at this compound very well, we can see that even if we are counting from, let's say, carbon 1, carbon 2, carbon 3, carbon 4, we get to realize that our longest continuous chain is still 4. Okay, even if we start from here as carbon 1, this becomes carbon 2, this becomes carbon 3, this will become our 4th carbon. So it means that whether we are counting from this direction or in the opposite direction, we still have 4 carbon atoms connected to each other. And we can see the same thing over here. 1, 2, 3, 4. 1, 2, 3, 4. That is 1, 2, 3, 4. Okay, so we get to realize that all these compounds are all butane, but it's just that their arrangements, okay, differ, but they will have the same physical and then chemical property. Why? Because the longest continuous chain for all these different frameworks are the same. Now there's something we need to note over here, something really important. So let me use red to indicate that. Now you get to realize that if we look at this is the longest continuous chain over here. So this is the starting carbon, let me use S, and this is the ending carbon, let me use E. Okay, so over here let me assume this is our longest continuous chain. Okay, because we want to form other possible structural isomers. We still don't want to have all the 4 carbon atoms connected to each other. So I'm assuming this is our starting carbon. Yes, this is our ending carbon. So in this case as well, this is our starting carbon, this is our ending carbon. So in this case again, this is our starting carbon, this is our ending carbon. Okay, so I'm using this as well for our starting carbon and our ending carbon. Don't mind the numbering in green over here. I'm just trying to have the longest, the straight chains that we have. I'm using them as the base. Okay, so which is we have the longest one over here, which is the horizontal one, is 2 here, here is 3, here is 3, and here is 2. Now what we need to note is the fact that the third and then the fourth carbon that we are adding over here, one is on the starting carbon and one is on the ending carbon, and this compound is still what? Butane. Okay, now for this guy, we have the fourth carbon on the ending carbon over here, and this compound is still giving us butane. Over here we can see that the fourth carbon is added to what? The starting carbon over here, and this is also butane. The same way, the third carbon and then the fourth carbon over here are on the starting and then the ending compound over here, okay, or carbons over here, and this is still butane. So what we need to note is that after writing our longest continuous chain, which is this compound, if you want to form any other different compound other than having the 4 carbon atoms connected directly to each other, we have to avoid adding the third or the fourth carbon atom to the ending or the terminal carbons. Let me take that again. For us to have a different compound which still has the same molecular formula, after drawing this longest continuous chain, we need to decrease the longest continuous chain by 1. If we do that, we need to avoid adding that last carbon onto the starting and then the ending carbon. This is an example. Let me write an example. So we can see that in this case, because we added the third and then the fourth carbons onto the starting and then the ending carbons over here, we still had the same compound. But what if this same compound over here, what if I write, let me say I decrease, after writing this, I know it's one of my possible isomers, I decrease the number of longest continuous chain by 1, so it becomes what? 3 carbons. So I have 1, 2, and 3. Now remember I said for us to have a different compound, let's avoid adding the 4th carbon to the terminal carbons over here. So instead of adding my next carbon, which is the 4th carbon, to either here or here, I decided to add it to the middle over here. Now let's add the hydrogens and see. Here we add 3 hydrogens here. Here is also 3 hydrogens. This guy will also take 3 hydrogens, and then this carbon over here, we just take 1 hydrogen. Alright, let's name this compound and see what we are going to get. Alright, so for us to get the name of this compound, we need to find the longest continuous chain. So our longest continuous chain in this case is going to be 1, 2, and 3. Note, you can count 1, 2, and 3 and then count this as 4, because this is not directly attached to this for it to continue the chain. So if you want to go the other way, this has to be 1, 2, and 3, but this will become a substituent. Okay, so I'm using the horizontal one as my longest continuous chain. Now if I do that, I get to realize that if I have 3 carbon atoms connected to each other, the parent name is what? Propane. So I write here propane. But I can see I have 1 extra carbon over here which is attached to the 2nd carbon. So which means this becomes a substituent. So it becomes what? This CH3 groups is what we call methyl. Okay, and this methyl group is on carbon 2 over here. So the name of this compound becomes what? 2-methyl propane. Now we get to realize that this name is different from the butane that we are having repeated over here at the top. But still, this compound has 1, 2, 3, 4 carbons in total. It has 3 hydrogen here, 3 here, 3 here, which is 9, plus 1, which is 10 hydrogens. This same compound that we kept getting butane when we try to change the carbon-carbon connectivity, we realized that when we stop adding the extra carbon over here, okay, which is the 4th carbon, when we stop adding it to the terminal carbons over here and we added it to the middle one, we had a different compound. So this is also 2-methyl propane, is also another possible isomer for C4H10. So this, let me take this. All right, so this is when we had 4 carbon atoms and they are in straight line. Okay, so what we did was we reduced the longest chain to 3, so we have 3 straight chain, and we realized that whether we add the methyl at the top over here or we add it at the bottom over here, we are still going to get 2-methyl propane. So from here, let's reduce the carbon atom to 2 and see what we can get. So we have 1 and 2. Okay, now we can see that in this case, if we reduce the carbon atoms to 2, okay, we realize that the remaining 3rd and 4th carbon that we have will all have to end up being added to these 2 carbon atoms. It's either we add the 3rd one here and add the 4th one here, or if we have these 2 longest continuous chain, we add the 3rd one here and then we add the 4th one here. Now, like I said we should avoid adding the remaining carbons after we shorten the chain. We should avoid adding the remaining carbons onto the terminal carbons that we have. So this is not part. Okay, now we realize that if we add, let me say this is the 3rd and then the 4th. If we add the 3rd one to the first 2 carbon atoms that I initially wrote and then add the 4th one to this one, we can see that this is also still 2-methyl propane. So which means in the end, for a C4H10 compound, we only have 2 possible isomers, and that is what? Butane, and then what? 2-methyl propane over here. Now I know this is a lot, so let's look at the next example so that we can digest well what I just said over here, and that way I will explain it even more further and much more simpler. All right, so for a 5 carbon alkane, we have a C5H12. All right, so first things first, without going sideways, first things first. So the first thing we have to do is to write down the 5 carbon atoms connected straight to each other. So we have 1, 2, 3, 4, and 5. So let's add the hydrogens. So we have these guys here. This guy will also be 3. Then we have hydrogen here, hydrogen here. Okay, so this is 5 straight chain. Okay, all right, so this is the first one that we have. Now after drawing this guy, you name it. So this is 1, 2, 3, 4, 5. That is the longest continuous chain over here is 5. So 1, 2, 3, 4, and 5. So this is what we call pentane. So this is a pentane molecule. Now after drawing the pentane molecule, if we try to change the structure of this compound so that we have another compound which we are calling isomer, we need to reduce the chain by 1 carbon. Okay, so by reducing the chain by 1 carbon, this is what we have. So the next one is going to be what? A 4 carbon straight chain. Okay, so for a 4 carbon straight chain, I'm going to have my carbons 1, 2, 3, and 4. So this is my 4 carbon straight chain. Now like I said, I have to avoid at all costs adding the 5th carbon over here to to these two terminal carbons over here. So let me write another one. So we have 1, 2, 3, and 4. Okay, so this is still a 4 carbon straight chain. Let me use another color to depict the hydrogens. All right, so for the 5th carbon, okay, I decided to add it over here in this case, and then for this guy I decided to add the 5th carbon over here. Okay, so I can now complete the formula by writing the hydrogens needed. So I write them here. This is 3, this is 3, here is 1, and here has to be 2. All right, so if we look at this compound really well, we get to realize that when we reduce the 5 carbon chain to a 4 carbon chain, we have our longest continuous chain here will be 1, 2, 3, 4. Here is also 1, 2, 3, 4. Okay, and we have the 5th carbon, okay, on a different carbon which is not the terminal carbons that we have over here. So we are sure that we are going to get a different compound. So let's look at the name of this compound. All right, so once we have a 4 carbon chain, we know that our parent name, okay, will be what? Bute. Okay, so this is what? Butane. Okay, now this is butane. We can see that the 5th carbon, okay, is on what? Carbon 2 over here of the parent chain. Okay, so this is a methyl group on carbon 2, so it becomes what? 2-methyl. Okay, so the name of this compound becomes what? 2-methyl butane. Now let's look at this. Now if you look at this really well, someone will be tempted to write what? 3-methyl butane, because you can see that the longest continuous chain is 4, and then we have this methyl group on carbon 3 over here. But that is wrong, because when naming alkanes, we need to give the substituent the least locant. So which means counting from this direction will be wrong in this case. So we need to count from here as carbon 1, carbon 2, carbon 3, and carbon 4. So this compound is not 2-methyl, it's not 3-methyl butane, but it is what? 2-methyl butane. Okay, so which means this naming is wrong and this is the right naming. So we get to realize that this compound and this compound are still the same. So which means if we shorten the alkane chain by 1 to get 4 chains, and we put the 5th carbon, okay, on carbon 2 or carbon 3, we get the same compound, which is 2-methyl butane, and that is as far as we can go for 4 carbon chains. So from here we have to reduce the chain again to 3 carbon chain. So let's do that. So we have 3 carbon straight chain. Let me write it this way. This is really not needed, I'm just writing them for tutorial sake. So from here, what I'm going to do is I'm going to write my longest continuous chain to be 3. Alright, so I'm going to write 1, 2, and 3. Alright, now that I have 3 continuous chain, I need to add the 4th and then the 5th what? Carbon atoms, because the compound is a 5 carbon compound. Now, like I said, I need to avoid adding the 4th and then the 5th carbon atoms to these terminal carbons over here. So which means the only option that I have left is adding the next 2 carbons to this middle carbon over here. So I'm forced to add the 4th carbon and then the 5th carbon to this guy in the middle over here. Okay, so when I do that, I can now add my hydrogens. Okay, so if you look at this is a totally different compound, and then let's name it and see what we have. So we have our longest chain over here will be carbon 1, carbon 2, and carbon 3. So we have what? Propane here. This is propane. Okay, So we can see that we have a methyl group over here. We have another methyl group over here. So we have two methyl groups, okay, on this propane long chain over here. So and both methyl groups are on what? Carbon 2. So we have what? 2 dimethyl. Okay, so we only add it to the propane to get the name of this compound. So this compound is what? 2 dimethyl propane. Okay, so let's reduce the chain further and see if we can get another possible isomer. So from here, let me reduce it to a 2 carbon chain, a 2 carbon straight chain. Now mind you, over here, because I said we need to avoid adding the extra carbons to the terminal carbons, we get to realize that if we had added it, we would end up getting either pentane or 2-methylbutane, which is just going back. So if you reduce the chain, add the extra carbon to any other carbon apart from the terminal carbons, and you get a new compound. So let me write I shorten the chain again to 2, so I have 1, 2. Okay, but there are 5 carbon atoms over here. So if I have 2 as my longest chain, you can see that in the end I'm forced to add the extra carbons that I have to one of these terminal alkanes, which means I'll end up getting one of these existing products that I already have. So if I add 1 here and I decide to add the remaining 2 over here, okay, and I add let me add the hydrogens. This is 1, 2, so 3 and 4, and yeah, so this is 3, 4, 5, 6, and this is also 6 years. So if I add it like this, I realize that my longest continuation will be 1, 2, 3, 4. Okay, so this is already, we are having butane. Okay, and we have a substituent on this carbon over here. Okay, so the fact that the substituent is here and it's on 3, and if we want to name this compound from counting over here, which is 1, 2, 3 and 4, we get to realize that this is on 2. This guy, if we are using the white, is on 3, so we give it the least locant, so it will be 2. So this compound will become what? 2-methyl butane, which is already what we have over here. So in summary, if we look at all the possible ways that we can draw a C5H12 compound, we get to realize that this guy will be marked, which is pentane. Okay, that is, we have a different name. This is pentane. So yeah, if we reduce the chain by 1, we have 2-methylbutane, 2-methylbutane. We only have to take 1. So this is also another possible isomer. If we further reduce the compound or the chain to 3 carbon, we have another compound here, which is what? 2,2-dimethylpropane, which is another possible isomer. And if we further reduce it, to a 2 carbon chain, we are already getting 2-methylbutane, which we already tick marked over here. So hence, I can now say that what? My C5H12 alkane hydrocarbon has 3 possible, okay, structural isomers. Okay, so, and those possible structural isomers are what? Pentane, 2-methylbutane, and then 2,2-dimethylpropane. Okay, so these guys are not part since they are already repetitions. So a C5H12 hydrocarbon has 3 possible structural isomer. All right, let's have a look at a 6,6 hydrocarbon and look at what we will get. All right, so for a 6,6, we will have 6,6H14. So let's look at the possible isomers that we will have. So first of all, like I said, write down the 6 carbon chains straight connected to each other. So we have, this is 6 carbon straight. Okay, so I'm going to have 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6. All right. So let me add the hydrogens. All right. So after having the 6 carbon chain, there's no possible other 6 carbon which will be this exactly the same as this. So I have to reduce the carbon atom to 5. So let's do that. So 5 carbon straight chain. Okay, so I'm going to have 1, 2, 3, 4, 5. Okay, so if I want to avoid adding the 6th carbon to this carbon and this carbon, it means I'm only left with adding the 6th carbon to either this guy over here, or this guy. Okay, so it means 3 possible compound can be formed from here. So let me draw all of those. So we have 1, 2, 3, 4, 5. Another one, 1, 2, 3, 4, and then 5. Okay, so over here I'm going to stop adding the hydrogens because that is wasting some time. So here I will be adding the 6th carbon over here to this guy, but in this case I'll be adding it to the middle guy here. This guy I'll be adding it over here. Okay, so this is the skeletal framework that we will have if we have a 5 carbon straight chain. So let me name this. This is hexane. This guy, okay, if we take this to be our longest continuous chain, this will be 1, 2, 3, 4, and 5. So which means the CH3 that we are now adding, which is the substituent, is on carbon 2 over here. Okay, let me do the numbering over here as well. 4, 5. So if we look at it, this is carbon 4 if we are counting this way. This is carbon 2 if we are counting in this direction. So we take the least locant. Okay, so this compound, okay, the longest continuous chain is 5, which is what? Pentane. Okay, and we have a substituent on carbon 2, so this will become what? 2-methyl pentane. Okay, now if we count this guy as well, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, we get to realize that from both sides, the substituent, which is the CH3 that we now have, which is our 6th carbon, is on carbon 3. Okay, so this becomes what? 3-methyl. Okay, our longest continuous chain is 5, so it's what? 3-methyl what? Pentane. Okay, here let me write the CH3. Alright, so if look at the third possible way of writing a 5 carbon chain with the substituents varying, we can see that we have carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. If we start naming in the opposite direction, we have 1, 2, 3, 4, and 5. We get to realize that this is carbon 4, this is carbon 2, so we give it the least locant. So this will become what? A 2-methyl, okay, pentane, which is something that we already have over here. So this is the same as this. Okay, so let's move on. Now this is still for 5 carbon straight chains. Okay, so from here we move to 4. So I have 4 carbon straight chain. So for the 4 carbon straight chain, I'm going to write my longest continuous chain to be 4. 1, 2, 3, 4, which means I have 2 extra carbons that I need to add. Okay, as usual, I will avoid adding it to these terminal guys, so it means I'm only left with 2 choice. Okay, it's either I add one of the carbons over here and then add the second one over here, or I have my longest continuous chain to be 4, and then I add both the fifth and then the sixth carbon to the second carbon over here, or I have this still the 4 carbon chain, and then I add it to this guy over here. Okay, so these are the three possible ways for me to draw a 4 carbon chain and distributing the fifth and then the sixth carbon atoms, and they will not be on the terminal carbons. So let's name these compounds and see if any of them are the same or they are different. So this is carbon 1, carbon 2, carbon 3, carbon 4. Okay, 1, 2, 3, and 4. So if we look at this, we have a substituent on, if we are using the down counting, we have a substituent on carbon 2 and then another one on carbon 3. So if we add the locants, that will be 2 plus 3, which is 5. If we are counting in this way, we have one on carbon 2 and then another one on carbon 3, which is still the same. So in the end, we have one on carbon 2, one on carbon 3. So we use any counting at all. So this compound, having 4 longest continuous chain, is bute. So it becomes what? Butane. This is butane. Okay. And then we have one carbon on carbon 2, another on carbon 3. So we have 2, 3 dimethyl, okay, butane. This is supposed to be close to each other. So let me erase that and write it well. Okay, so 2, 3 dimethyl butane. So that is the name of this compound. If we look at this guy, if we are naming from the top, we have 1, 2, 3, 4. From the down, we have 1, 2, 3, and 4. So if we look at the counting, we realize that the top counting will favor us and it will give us the least low count, because both the carbon atoms, the fifth and then the sixth one, are both on carbon 2 over here. But if we are going the opposite way, they will be on carbon 3, which will not favor us. So we'll go for the least low count, which is the 2 over here. So this compound becomes what? 2,2-dimethyl. 2,2-dimethyl. This is it group bute. So this is also what? Butane. Okay, so we can see that this is 2,3-dimethyl butane. This is 2,2-dimethyl butane. They are different compounds, so yes, it's acceptable. Now, if we want to look at this compound, we have 1, 2, 3, 4. Here is 1, 2, 3, and 4. We get to realize that if we want to take the top counting, we will have the 2 methyl groups on carbon 3, which is not going to favor us. If we take the down counting, it's going to be on carbon 2, which will favor us. So we'll end up getting what? 2,2-dimethyl butane, which is already what we have over here. So this is the same as this. So I'm going to erase that so that we can have space to work. Alright, so we realize that if we reduce the carbon chain to 4 carbon, we only have 2 possible isomers. Okay, so we move on. Let's further reduce it to 3. So 3 carbon straight chain. Let's see if we can have any possible isomer over there. Okay, so for a 3 carbon chain, we have 1, 2, and 3. So we have 3 as our longest continuous chain, and we need to add 3 more carbon atoms, but we want to avoid adding it to the terminal as much as possible, because if we add it to the terminal, we will end up getting one of these already existing products that we have. So let me add my 4th one over here, my 5th one over here. Now if I look at this, I'm forced to add my 6th carbon to either this carbon or this carbon, because carbon can only take what? 4 bonds. Okay, so already the middle carbon here has 1, 2, 3, 4 bonds surrounding it. So it means the 6th one cannot come to this guy, but it has to go to either this guy or this guy. Okay, so let me give it to this guy in this case. Now if I give it to that, you get to realize that when you are naming this compound, okay, with the hydrogens there, if you are naming this compound, our longest continuous chain will no longer be 3, it will become 4, which is 1, 2, 3, and 4. Okay, and you get to realize that the substituents are on what? Carbon 2 and carbon 2. So it will become 2,2 dimethyl butane, which is what we already have over here. And if we are to reduce this 3 carbon chain to 2 carbon chain, we get to realize that we will still be forced to add the extra carbons to the terminal carbons. Okay, so it means that we can only shorten this chain to 4 carbon chain and have different products. If we shorten it any further, we are going to get the same existing product that we already have. So in all, let's count the number of possible isomers for a for a 6 carbon alkane. So the first one we have is what? Hexane. So this is a product. The next one we have is this is a 2-methyl pentane. It's also a product. Okay. The next one is 3-methyl pentane, which is also different. So this is also a compound. So this guy is also included. Okay. This is 2-methyl pentane. It's already here. So let's cancel this guy. It's not part. If we look at this, we have 2,3-dimethyl butane. This is another compound. Okay. If we look at this, this is 2,2-dimethyl butane. This is also another compound. So in all, we have 1, 2, 3, 4, 5. 5 possible isomers for a 6,6H14 molecular formula compound. So the 1, 2, 3, 4, 5. Sorry, the 5 possible isomers are hexane, 2-methyl pentane, 3-methyl pentane, 2,3-dimethyl butane, sorry, and then 2,2-dimethyl butane, as we can see in this example. So here is the trick. The trick is, first of all, write the molecular formula, okay, which is what you have over here, and then write the longest continuous chain to be 6, and that becomes one of your possible isomers. Now after that, reduce the number of carbons or your longest continuous chain by 1. So from 6 you move to 5. So you write the 5 chain. Okay, now you avoid adding your remaining carbon to the end of the chain to avoid going back to your already existing 6 carbon longest continuous chain. Now the remaining carbon that you have, add it to the middle carbons. Okay, try to alternate it and see if you get a different name for the compound. So in this case, when we added it to this carbon over here, we realized we have 2-methyl pentane. When we added it to the middle guy over here, we had 3-methyl pentane. When we added it to the ending second to last carbon over here, we get to realize that the naming, okay, if we take into consideration the least locant, it will still be 2-methyl pentane, which was something that we already have. So we ignore that because it's still, even though it's a possible isomer, we already have it, so there's no need we repeat it twice. Now, which means we are done with 5 carbon chains, so we further reduce it to 4. So if we do that to 4, we are going to have this guy, okay, these 2 guys as possible isomers. Now the next example is supposed to be 6,7, that is 6,7H16. Let me use white. Okay, but because this tutorial is already long, okay, I'm going to give you the number of possible isomers that we have for this compound. So this compound, which is let me rewrite it again, 6,7H16, okay, has 8 possible isomers. Okay, so it has 8 possible, okay, isomers. So try your hands on this compound, okay, on this molecular formula. Try and see if you get 8 possible different compounds which have the same molecular formula. So first of all, you write the 7 carbon chain, and then you reduce it to 6, and then you try to add a 7th carbon to the middle carbons in your longest continuous chain to see if you have different products or different compounds. After you are done exhausting that, further reduce the carbon chain to 6. Now the remaining, to 5. The remaining 2 carbons, try to add it to the middle again, then reduce it to 4, try to add the remaining carbons to the middle ones again, and then you will end up having 8 different possible compounds that all have the same molecular formula as this. So thank you so much for watching. I hope you try our example over here and see if you can get the 8 possible isomers that we have. Okay, so thank you once again for watching, and I will see you in the next video. Bye bye.